Dear colleagues, dear friends, welcome to the optimization seminar. So our speaker today is Geovani Nunes Grapiglia from University of Leuven in Belgium. He received he's from Brazil and received his PhD in 2014. So if I'm not wrong, since I found some information in Portuguese from the University of Paraná under supervision, and it was very surprising to me, of Yaxiang Yuan from Beijing. I hope this is correct. And yeah, after being postdoc in the same university, he moved, so Geovani moved to Belgium. So working in the research group of Yuri Nestero in the framework of his ERC advanced grant. And now he's on assistant professor position to the same university. So thank you for accepting our invitation. I was very much impressed by the publication record of our speaker. So many good papers in many good journals. So the floor is yours. You have 45 minutes for a talk.
Thanks, Professor Bort. Thanks for the invitation, for the opportunity to speak in this seminar. Just one remark is that my PhD advisor was Professor Jingyun Yuan, Chinese, but living in Brazil, and Professor Yaxiang Yuan was my co-advisor.
Okay.
Just one remark.
Thank you for clarifying this.
Yes, if I don't mention Professor Jingyun Yuan, he will be sad with me.
My mistake. Sorry for that. Okay.
So today I would like to present some methods, derivative-free methods, based on finite difference gradient approximations. Okay, so I would like to present some new results about a very old technique for derivative-free optimization. And I divided this talk in three parts. So first I will introduce the problem and the motivation for this work. Then I will present the new methods. And finally, I would like to show some preliminary numerical results. So in this work, I'm interested in the unconstrained minimization of a function f. And I'm assuming that f is a non-convex function with domain being Rn, okay, bounded below by some number, f low. And I will assume that the gradient of the function f is Lipschitz, okay? And here I am in the context of derivative-free optimization. So what does that mean? It means that we want to approximately solve this problem, but relying only on functional evaluations. So I'm assuming that for some reason, I'm not allowed to compute the gradients of this function, okay? And of course, although we don't compute the gradients, we expect to have methods or to develop methods that are able to find approximate critical points. Okay, so given some epsilon, we want methods that are able to generate X bar such that this inequality is satisfied for any starting point. So we have these iterative schemes that are globally convergent. Okay, and however, in the context of derivative-free optimization, we are interested in the number of functional evaluations that we need to perform to get epsilon approximate critical points. So in this type of problem, functional evaluations, they may be very expensive to compute. So it's not true that the method that takes less iteration is necessarily the fast one, because it depends on the number of functional evaluations the method uses. So in this case, the theoretical question that is relevant for us in the analysis of the method is this question about the evaluation complexity of the method. So what we want is to estimate how many functional evaluations the method needs in the worst case to find X bar satisfying this inequality too. Okay, and the upper bounds that I'm going to get, in this sense, I will call worst case evaluation complexity bounds. And of course, several methods have been already analyzed in this sense. Okay, And I divided here the description in two groups, deterministic methods and randomized methods. So for deterministic derivative-free methods, bounds of order n squared times epsilon to the power minus 2 have been obtained already for some classes of methods, for example, for direct search methods and also for model-based trust region methods. These methods based on interpolation models, okay? And as you can see here, the complexity bound depends on the problem dimension and of course on the precision that you want, this number epsilon, okay? And the dependence in the problem dimension is of this type, it's n squared. And of course, we would like to get methods with better complexity. In particular, we would like to get methods with a better dependence in time in terms of n. And this goal was achieved recently by using randomized techniques. So we have this class of randomized methods in which some elements in the method, they are computed in a random way. So we may have, for example, random steps or random directions or even random subspace that are used in the method. And using these techniques, it's possible to improve the evaluation complexity of the methods. So I mentioned here some works where you can see that the dependence in terms of the dimension is linear. Okay, so we can get something better using these techniques. However, in terms of the theoretical results and the complexity bounds that can be obtained, these bounds, they are obtained in the sense of the expectation or in terms of a high probability, okay? Not like for deterministic methods, where we really can bound the number of function evaluations to find an epsilon critical point. So the motivation for this work was to investigate this question. So the main question was, is it possible to design deterministic derivative-free optimization methods with an evaluation complexity of order n times epsilon to the power minus 2? So that was the motivating question, okay? Obtain deterministic methods for which we can prove evaluation complexity bounds having linear dependence in terms of the problem dimension, okay? And in this talk, I'm going to show you that the answer for this question is yes. And in fact, we can get that using, I think, one of the oldest techniques for derivative-free optimization, which is the use of finite-difference gradient approximation. Okay, so now I would like to describe these methods to you, to explain the main elements of the methods. And to do that, I think one good way is to tell you step by step how I obtained the methods. Okay, so I will describe step by step how the methods were obtained. And in this way, I hope you can get the main ideas about these techniques. So of course, as usual, we don't start from scratch. We start with some existing elements in the optimization theory. So I consider here as my starting point as a template, a line search method, okay? A derivative-based line search method. So this is a very simple method, okay? So I will describe here just for you to get familiar with my notation and the way how I'm presenting the methods. So this is just a gradient method with line search, or a generic gradient method with line search. So we give x1 and a parameter sigma 1 bigger than 0, okay? And we compute then at the kth iteration a trial point, sorry, x plus as xk minus a step size times the gradient, right? So at the beginning of the kth iteration, we use this I equal to 0. So what does that mean? It means that the first step size that we try is 1 over sigma k. Right? So you can see that this sigma k, with this sigma k, we try to approximate the Lipschitz constant of the gradient of the function, which is assumed to be unknown. And if this trial point satisfied some kind of line search condition, some descent property, we accept the point. And we define xk plus 1 as x plus, okay? And for the next iteration, we may also decrease this parameter sigma to give to the method a chance to perform a larger step in the next iteration. And of course, if the line search is not satisfied, what we have to do is to decrease the step size. And we do that by increasing I. So by increasing I, we have this denominator here, it will increase. So this means that the step size will decrease. And we keep doing that until some line search condition is satisfied. So this is just a generic description of a line search gradient method. Okay? And of course, this is not what I want, because this method relies on the gradient of the function f. So I'm not allowed to compute that in the derivative-free setting. So I have to approximate this gradient somehow. And a very simple way to do that is to use finite difference. Okay? And that's what we are going to consider here. So I will approximate the gradient using forward finite difference. So here, what we do at step 1 is to choose this parameter hi, which will define the finite difference approximation. And then we get this vector gki. This is my approximated gradient. And then in the computation of the trial point, instead of using the true gradient, now we use this approximated gradient. Okay? And all the rest will be the same. So we need some kind of line search condition to decide when the trial point is good. Okay, and then if this line search condition is satisfied, we accept the trial point, and otherwise we decrease the step size and keep doing that until the line search condition is satisfied. And you can see that still this is just a generic method, derivative-free method, because what is crucial here and essential is how we choose this parameter hi, which is used in the forward finite difference formula, and also what is this line search condition. Okay, so we need to use some concrete line search condition. And so let's start with the choice of hi. And actually the inspiration or the idea for the choice of hi in this work, it comes from adaptations and variations of the cubic regularization of the Newton's method. So this is a second order method, which has very nice complexity results, and it uses the Hessian. Okay, and recently some researchers have considered the replacement of this Hessian by some matrix bk. And then the question is what conditions we should impose on this bk in order to have the same complexity bounds that we have for the standard cubic regularization of the Newton's method. And recently, Kohler and Lucci, and also Wang and collaborators, they proposed and suggested the use of this condition. So we have the error between the Hessian and this matrix bk is less than or equal than some parameter kappa b, which can be selected by the user, times the previous step size. Okay, so this means that this right-hand side here, it is computable. At the beginning of the iteration k, we know this right-hand side. So this means that we can think about ways to construct the matrix bk in order to satisfy this inequality. Okay, this in the context of second order methods. So here it would be some kind of first order implementation of a second order methods if we use only first order information to get this matrix bk. Of course, so a natural condition that we can consider in the context of derivative-free optimization is this one. So it's a similar condition, so inspired by this condition 3. What we want here is a condition like this. We want an approximation for the gradient that with an error that is less than or equal than some kappa g times the previous step size. okay? And remember that we are assuming that the gradient of the function f is Lipschitz. And in this case, we can actually bound this error. And we have a formula for that. We have an inequality. We know that the error between the true gradient and the approximated gradient obtained with forward finite difference is less than or equal than the square root of n times the Lipschitz constant of the gradient divided by 2 times hi. Hi is the parameter that we use in that forward finite difference formula, okay? And you see that now, if we compare these two inequalities, we can choose hi in a way that gives us this inequality form. And for that, it is enough to take hi less than or equal than 2 times kappa g divided by the square root of n times L times the previous step size, okay? So if we take hi sufficiently small in this sense, we have this inequality. And of course, in this scenario, I'm assuming that I don't know L. I don't know this Lipschitz constant. So what we can do, we can just replace this L by the inverse of the step size that we are using in our method, which is 2 to the power I times sigma k, right? So by doing that, if this inverse of the step size is bigger or equal than the Lipschitz constant, then this inequality will be satisfied, and therefore this inequality 4 will be satisfied. So the inequality that we want will be satisfied if we take hi like this, and this parameter, this number is bigger or equal than the Lipschitz constant of the gradient. So this gives us a formula for this hi, the parameter that we use here to compute the approximated gradient. And so now what remains to explain is what is this line search condition. So when we say that this trial point x plus is good enough. And for that, we have a lemma. So if we compute this x plus, just like we do in the method that I described to you, and if we have that inequality, that error bound for the gradient, where here we have this kappa g times the previous step, step that was performed by the method. And if this 2 to the power I times sigma k is sufficiently big, we can show this inequality, okay? So this is not exactly what we wanted or what one would expect, because you see that here, of course, we have a lower bound for the difference between f of xk and f of x plus. But usually in a line search condition, at least in a monotone line search condition, we have a positive lower bound. And this is not the case here, okay? But anyway, we are going to use this inequality. So we just replace this inequality in the method. And as I was saying, what we have here is this second term in red, and just forget about this term, suppose it does not exist. If we had this inequality, you see that we would accept steps that give a decrease in the objective function. So we would have f of xk plus 1 less than or equal than f of xk for all k. However, because we are subtracting this positive term here, using this inequality as acceptance condition for the trial point, it may happen that we may accept a point x plus that has a function value bigger than f of x. So this means that the sequence of function values at the iterates of the method, it may behave in a non-monotonic way, right? So you can consider this line search condition as a type of non-monotone line search condition. And this, of course, has some advantage, some disadvantage, but this is what we can get here. And so you see that the method is almost defined. So what remains is to choose this parameter kappa g. So we have freedom to do that. And here the idea is to anticipate the complexity analysis of the method. So if you are familiar with the complexity analysis of line search methods, and you know that what we do, one of the very first steps for the analysis is to sum up these inequalities. Okay, and then here for the left-hand side, we have a telescope sum, and so we use the lower bound for the function value, and then we have an upper bound here in terms of f of x0 and these f low and so on. And then here we would like to have a sum in terms of this square of the step size. But for that,
I have a question.
Yes,
so,
you can ask.
So before doing so, is it easy to see that one will jump at some point to step 2?
Yes, because of the lemma. So we know that if this 2 to the power I times sigma k is sufficiently big, let me just go back to the lemma. If this is sufficiently big, the inequality will be satisfied.
Okay.
And if we go back to the method, what we do when this inequality is not satisfied is to increase this I.
Yes.
So we keep increasing this, and at some moment, we will have this number bigger or equal than 2 times L plus kappa G.
Okay, yeah, thank you.
Is it clear?
Excuse me.
Yes.
Can I also follow up a question on that, or?
Yes, sure.
On step 1.2, you define xki plus.
Yes.
On step 1.3, you're minusing that with x of k. Wouldn't that cancel x of k in there and 2I sigma k cancel out?
Sorry, I didn't.
So you see
well
step 1.2.
Yes.
You have a definition for xki.
Yes.
Can you just replace the xki in a step 1.3 with that definition, and it's simplified?
Yes, you can, and then you will have this term here, the step size,
and then
times
that
the
term,
ki.
Yeah, but that term multiplier, I'm assuming it's a scalar, right?
Yes.
So that wouldn't cancel with the 2I sigma k?
No, because we have the square here.
Oh, I didn't see that. Yeah.
Okay.
Okay, perfect.
All right.
But we can do this replacement, right?
Yes, you can do for sure. And
thank you.
You're welcome. Thank you for your question. So what I was saying is that the method here, it is almost complete. So what remains is the choice for kappa G. And I'm trying to say that I will choose this kappa G because I already know what I will do in the complexity analysis, what I need in terms of inequalities, and what I need is these two terms, they have to be comparable. So the first thing is to consider kappa G equal to sigma 1 divided by 2. And here I will have already this denominator 4 for both terms. And the second thing I'm going to do is regarding the choice of I. Here at the very beginning, so we start with I, okay? I equal to 0. And I will change this a little bit, and I will start with I being the smallest integer, bigger or equal than 0, such that this number, 2 to the power I times sigma k, is bigger or equal than 2 times sigma 1, okay? And so this will make these two things comparable and will make easier the complexity analysis. And also the nice thing about this is that it will impose a lower bound for the sequence sigma k, as we are going to see, I think in the last slide, yes. So the first lemma for the complexity analysis is this lemma that gives us bounds for the sequence sigma k, right? So that's step 1, the choice of the first I gives this lower bound to us. So sigma k is bigger or equal than sigma 1. And we also have an upper bound. So sigma k is less than or equal than 2 times L plus sigma 1 divided by 2. So this is just our kappa G, okay? So we have this upper bound sigma max, which is independent of the problem dimension. This is important. So it depends only on the Lipschitz constant and sigma 1 divided by 2. And using these bounds, what we can show is that we have an upper bound for the number of function evaluations that the method performed up to the iteration t. Okay, so I'm denoting this number by fe of t. So this is the number of function evaluations that we perform, the method perform up to the t iteration. Okay, and this number is of order n times t, which is very intuitive because each approximated gradient using that forward finite difference formula requires n function evaluations. Okay, so it's very natural that if we perform t iterations of that method, this number of function evaluations will be bounded by something of the order n times t. All right. So you see that using this result, now all that remains to us to get an evaluation complexity bound for the method is to bound the number of iterations that we need to find an epsilon critical point. Okay, if we have a bound for this t, where t is the first iteration such that the norm of the gradient of xt is less than or equal than epsilon, then we can just plug that bound here to get this evaluation complexity bound in terms of function evaluations. And that's what we have here in this theorem. Okay, so if we say that t is the first iteration index such that the norm of the gradient of f at xt is less than or equal than epsilon, what we can show is that t is bounded by a number of order epsilon to the power minus 2. And here again, what is important is that this constant that is multiplying here epsilon to the power minus 2, it does not depend explicitly on the problem dimension. Okay, and so you see here we have the Lipschitz constant, and here the functional residual, and here sigma 1, x1 minus x0, and here sigma max. And remember that sigma max is just depending on L and sigma 1. Okay, does not depend explicitly on the problem dimension. And as a consequence of this, if we combine the previous lemma with this theorem, what we have is that we know that we have already a bound for the number of function evaluations up to iteration t, which is of order n times t. And now if we consider this bound for t, what we have is an evaluation complexity bound of order n times epsilon to the power minus 2. Okay, so in this case, we get this evaluation complexity bound with linear dependence on n, on the problem dimension, which is what we wanted. Okay, and of course, we have several components in this method, and you may wonder what is the main trick? What's the reason why for this method it is possible to obtain this improved complexity bound? And it turns out that the main trick here is the use of the problem dimension in the method. Okay, so remember that in the formula that we are using, our choice for hi, that parameter that we use in the forward finite difference approximation, we have here in the denominator the square root of n. Okay, and this is the key component to obtain this improved complexity bound, and I will explain to you why. So remember that for forward finite difference, we have this error bound in terms of hi. Okay, and we could, in principle, to consider hi like this. We could just replace, not use the problem dimension in the formula. We can use just replace the square root of n by 1. Okay, no problem with that. This is a feasible choice for hi. But what happens is that now to obtain the inequality that we want, to make sure this inequality is true, what we need is 2 to the power I times sigma k to be bigger or equal than the square root of n times L. Okay, and remember that before, this square root of n didn't appear in the lower bound. We just needed this number to be bigger or equal than L. But if we do not consider this number in the formula for hi, we need to consider here in the lower bound. And this lower bound, actually, it gives us the upper bound for sigma max. Remember that sigma max, which is the upper bound for sigma k. Before we had the sigma max that was independent on the problem dimension. But now, in view of this inequality, what we have is a sigma max that is of order of square root of n. And of course, we could carry on the analysis in the same way, and we would get an iteration complexity bound, an upper bound for the number of iterations to find this epsilon critical point, just like we obtained before, okay? So we have this bound of order epsilon to the power minus 2, but we have sigma max here. And we have sigma max here in square. So this bound actually is a bound of order n times epsilon to the power minus 2, okay? Because we have the square root of n, and then we take the square. And now if we plug this in the bound for the number of function evaluations up to iteration t, you will see the problem. So we know that the number of function evaluations is bounded like this, is bounded by a number of order n times t. But now if t is bounded by something of order n times epsilon to the power minus 2, we have n here times n here, and you see that we get this n square, just like in the existing bounds for deterministic methods. So I hope with this description, it is clear that the key trick here, the main trick, is the use of the problem dimension in the method. Okay. So this is what allows us to get this better evaluation complexity bound. All right, so I described to you the very simple method which was inspired by this gradient method with line search, but we can try to do something better in terms of the choice of the trial points. Okay, the computation of the trial points. So instead of computing x plus as xk minus the step size times the approximated gradient, we can, for example, compute this x plus as an approximate minimizer for this quadratic model, okay? So where this matrix Bk is a symmetric and positive semi-definite matrix. So this case here that I just described to you corresponds to the case in which Bk is equal to 0, right? And then this number that keeps showing up, 2 to the power I times sigma k is just the regularization parameter. And we can do that. We can use this model. And actually, we don't need to minimize it exactly. We can consider an approximate minimizer for this model. And this will gives us a suitable trial point, okay? And in terms of the matrix Bk, we can compute Bk using some quasi-Newton formula, for example. Of course, in the quasi-Newton formula, if you remember, you have to consider this difference of gradients. And here, of course, we are going to consider difference of these approximated gradients obtained with finite difference. Okay, just to try to capture some second order information. And if we assume that the norm of these matrices is bounded, we can get the same complexity bound. We can get this order of n times epsilon to the power minus 2. Okay, so this is this gives us this quadratic regularization method. And of course, all these methods that I described to you, the quadratic regularization, also this gradient method with finite difference, approximated gradient, I use it for finite difference. And of course, you may wonder, what about central finite difference gradient? Because they would give us a better approximations for the gradient, and why not? And in fact, we can use them. We can obtain methods using central finite difference, just like we did before. So remember that our target inequality is this one, in terms of the error between the true gradient and the approximated gradient. And it turns out that if we assume that the Hessian of the function f is Lipschitz continuous with constant L2, we can prove a better error bound when we use central finite difference. We can prove a bound, an upper bound of equal to square root of n times the Lipschitz constant for the Hessian divided by 6. And here the dependence in terms of HI is better because here we have HI squared. Okay. And of course, we have this inequality, we have this. So we can obtain the inequality that HI should satisfy so that we get inequality 5. So if HI is sufficiently small, is less than or equal than this number, so here we have the square root of this number here, and in the denominator, we have now the Lipschitz constant for the Hessian. So if HI is small like this, we have this inequality 5, okay? And once again, so before we assumed that we didn't know the Lipschitz constant for the gradient. And now also we don't know usually the Lipschitz constant for the Hessian. So we replace this guy here, this L2, by the inverse of our step size, okay? This 2 to the power I times sigma k. And that's it. That's our choice for the parameter that we are going to use in the central finite difference gradient. Okay, and as you can see, if this number here is bigger or equal than this Lipschitz constant for the Hessian, we can ensure the inequality that we need. Okay, our target inequality, and we can get the same an evaluation complexity bound of the same order. This n times epsilon to the power minus 2 for this method. However, in this case, we have to assume that the gradient Lipschitz and the Hessian Lipschitz. Okay, so we are considering a more restrict problem class. We have to assume more about the function. But we have this variation of the method based on finite difference, central finite difference. And so now I would like to show you some preliminary numerical results. Of course, this is nice. We have these methods. They have improved complexity bounds with respect to existing deterministic methods for derivative-free optimization. But it is interesting to see how they behave in practice. Okay. So these numerical experiments, what I did was to consider a set of nonlinear least square problems from this very standard collection of Murray, Garbo, Hilson problems. Okay, and I consider all the problems in this collection in which the dimension n can be chosen. Okay, and then for each problem, actually, by problem here I mean the function, the objective function in this test collection. For which each of these functions I consider two choices for the starting point. So the starting point x0, which in this case it should be x1, is equal to 5 to the power s times x bar. And s is either 0 or 1. And this x bar is the standard starting point that is given in this collection. Okay. And I also consider 4 dimensions, 8, 12, 16, and 20. Okay, so this gives me a total of 120 test problems. So this is the total number of problems that were considered in the tests. So for the first experiment, what I did was just to implement that very simple method, the one with bk equal to 0 and forward finite difference gradient. Okay, and I'm calling this code by FDGM. Okay, finite difference gradient method. And what I did was to apply to a subset of this large set of 120 problems. I just consider n equal to 8 and the choice s equal to 1. Okay, so this gives us 15 problems. Okay, and what I wanted to evaluate or to investigate is the ability of this code to generate approximate stationary points. So all these results, they are about the ability of the method finding these epsilon critical points. So although I don't use the gradient in the method, because in this case I have access to the code of the gradient of all the functions, I endow the method with this stopping condition. Okay, so just to see if the method is really finding stationary points. And just some notation, I'm going to present you a table. So let me just define these terms. So I will refer as T of epsilon, the number of iterations required by the solver to generate a point satisfying this inequality. So this is about the number of iterations. Fe of epsilon corresponds to the number of function evaluations, okay? And I will also consider this strange number here, okay, this A of epsilon. So this is Fe of epsilon divided by T of epsilon times n plus 1. And why I'm going to consider this number, why it is interesting, let's just remember the first lemma that I showed you, the lemma that gives us an upper bound for the number of functional evaluations performed up to the iteration t. So we have this upper bound here, 1 plus n plus 1 times 2t plus this difference of logs. And if we divide everything by t times n plus 1, you see that what we get is this, I will call this number a of t. And we have that this fraction is less than or equal than 2 plus this number divided by t times n plus 1. So this means that this number a of t is bounded by something that approaches to 2 when t goes to infinity. Okay, so for large values of t of epsilon, the prediction from the theory is that the corresponding number a of epsilon should be close to 2. And this is exactly what we see in this table. Okay, so you see that here I consider epsilon equal to 10 to the power minus 1 and epsilon equal to 10 to the power minus 2. You can see that for all these 15 problems, the code FDGM was able to really find epsilon critical points. And here's the number of iterations. You see that it is quite reasonable in the context of derivative-free optimization. For the number of functional evaluations, it's also something reasonable. And if we look at A of epsilon, you see that for many problems, it is close to 2. Okay, but in some case, it is bigger than 2. It's 4, it is 7, and so on. So maybe this means that the theory is not very, very accurate. But if we just plot these pairs, T of epsilon and A of epsilon, we see that the prediction from the theory is correct. So we really see what the theory predicts. As T of epsilon becomes larger and larger, this A of epsilon becomes close to 2. Okay, so this illustrates the theoretical result that was proven. And in the second experiment that I would like to show you, I compared several versions of these methods. Okay, so I already talked about this FDGM, which is the forward method based on forward finite difference, and with BK equal to 0. Okay, and now I will consider also this FDBFGS. I'm sorry, all these names, they are terrible, but it's just to make a difference between the methods. So this is just an implementation of that method that I described to you, but with the matrix BK obtained using BFGS formula. Okay, and again, forward finite difference gradient. And the last code is this FCBFGS, which is based on central finite difference gradients. And BK, again, computed using BFGS formula. And what we have here is something called data profiles. So each line corresponds to one of the methods. Okay, so the red line, we have this forward finite difference with BFGS. The black line is the method based on central finite difference with BFGS also. And this blue line is just the simple code, this FDGM. And here what we have is the percentage of problems that are solved as a function of the number of functional evaluations performed by the method. Okay, so in summary, the higher is the line, the better is the method. Okay, and we see that as expected, the methods that try to approximate second order informations, that they are better than the simple method. And also we see here that the method based on forward finite difference is better than the method based on central finite difference. So although the central finite difference, they usually gives us better gradients, this means that or we can see in practice that the method usually needs less iterations, okay, to find a point with the same quality of the method based on forward finite difference. However, central finite difference, they are more expensive in terms of functional evaluations. So, and the benefit that we have in terms of number of iterations is not, does not compensate the high cost in terms of functional evaluations to get these approximated gradients. Okay, and just to conclude, I would like to show you one more data profile. Now I compare this FDBFGS, which was the best method, that the best version of these new methods that I described to you, with two existing derivative-free solvers. One is a model-based derivative-free truss region method from a previous paper that I wrote with Professor Jin-Yong Yuan and Professor Jiaxian Yuan. And the other code is an implementation of the Nelder-Mead method. And as you can see here, again, this method based on finite difference seems to be very efficient. So it was better than the model-based truss region, and it was better than the Nelder-Mead method. Okay, so what we have in this work that I'm describing in this talk for you is what we have deterministic quadratic regularization derivative-free methods. The nice feature about these methods is the improved evaluation complexity in terms of the problem dimension. So we don't have any square here anymore. We have a linear dependence on the problem dimension. And the preliminary numerical results seem promising and gives motivation to keep doing research in this area. So of course, topics for future research is, one topic is the generalization of this approach for composite non-smooth optimization, in which the objective function is a composition of psi and a function c, where psi is non-smooth. And of course, noisy problems. So recently, a lot of progress has been made in terms of noisy problems and derivative-free optimization. It would also be an interesting direction to look. So if you are interested in this work, and you can check the preprint, which is available on Optimization Online. And I would like to conclude by wishing to everyone a very happy and healthy Lunar New Year. So thank you very much for your attention.
Thank you very much for a very clear and interesting talk. Yes, are there any questions? So then let me ask the first question. You mentioned as a possible future research the composition of a non-smooth function, which is a smooth function.
Yes.
So how would you approach?
Yeah, so then we can, what happens is that we have already truss region methods, derivative-free truss region methods for these composite problems. And these methods, they work like this. So what we do is to consider interpolation models for the function c of x. Okay, we consider linear interpolation models for the function c of x.
Okay, yes.
And these models, of course, they have to, we need to ensure some error bounds in terms of the Jacobian of this function c. So a natural way to approach this using this finite difference is to consider these linear models for c, but constructed using finite difference and with this careful choice for hi.
Okay. Thank you.
Thank you for the question.
The other questions? Yes, Bruno Lorenzo.
Okay. Thank you very much for the very nice talk. So one thing I didn't actually I'd like to confirm. So I understood that in the experiments, so you considered that stopping condition at the gradient just to check if it's indeed getting a stationary or something close to a stationary point. But I imagine that, for example, in application, where you actually don't have the access to the gradient, what would you use? What do people usually do in this case? So they just run the method a bunch of for some time and see. Or what I'm trying to ask is there an indirect way of checking stationarity? So when you don't have access to the gradient in this context.
Yes, that's a very good point, Bruno. So we can consider several stopping conditions. For example, you can sometimes you have only a limited budget of function evaluations. This gives us a very clear stopping condition. So once you reach the maximum that you can do, you stop. And another stopping condition is in terms of the progress that you are doing with respect to the function values. So if for a certain number of iterations, you see that no progress is being done in terms of the improvement of the function value, you can stop the method. And another condition would be to check the step size in this case, in particular for this method. So if you have this xk minus xk minus 1, very, very small, smaller than some threshold, you can also stop the method.
Okay. Yeah. So you can check if there is no progress between successive iteration. Okay.
Thank you. So, Daniel, you have another question. So, please.
Hey, thank you for the really interesting talk. I just have a fairly straightforward question. Did you also consider the convex case, and could you show, would you achieve order n to the epsilon n times epsilon to the -1 function query complexity for finding the approximating the minimizer, finding an epsilon solution to a convex function? Thank you.
Yes, thank you for this question. It's actually very interesting. And yes, what I can show now is this bound of epsilon n times epsilon to the power -1, but only for that simple version of the method. When I put bk in the history, it becomes complicated, and I don't know yet how to get this bound.
Mm-hmm.
But for the simple version, it can be done.
Cool. Thank you.
Thank you. Are there other questions? So I have a curiosity. So, the fact that one approximates the Lipschitz constant by something for which powers of 2 are used. I mean, why powers of 2? I mean, yeah. What is special with that?
I think there's nothing special. It's just an statistical choice for statistical reasons. It could be any number bigger than 1.
Okay. Yeah, of course. Yes. Okay. But okay. So, but this is, I mean, yes, good. So, but okay. Thank you. So, the other questions. So then let us stop here. Thank you very much for a realistic, very clear talk. So yeah, I learned a lot about these techniques. So I just want to announce that we will post the slides of the talk and the video on our website, and that our next speaker will be Patrick Johnstone from Brookhaven National Laboratories next Monday, same time. So I want to wish you a great afternoon and a fantastic week. And yes, and also to probably, we don't have today so many Chinese colleagues in the Zoom room, but I want to wish them a happy New Year of the Tiger. So all the best.
Thank you very much.
See you next Monday. Bye-bye.